Good afternoon, everybody. My name is Mason Patterson with Cape Fear Community College in Dr. Hans Chapman's EGR 214 Numerical Methods for Engineers class. This is my fall 2023 final project on Python solutions for Newton Raphson method root finding. First off, the Newton Raphson method is a powerful iterative technique for finding roots of a function. Let's explore its formula and visualize how it works, and we'll even look at a couple of examples. The Newton Raphson method gives us the first derivative of a function at a given point to iteratively refine our estimate of the root. The formula is x root is equal to an initial guess minus the function over the derivative of the function. This expression updates our guess based on the function value and its derivative. Imagine starting with an initial guess for x and considering the slope of the function at that point. By using the derivative of our function, we can iteratively refine our guess. The core idea is to subtract the ratio of the function value to its derivative from our initial guess. Repeating this process gives us a more accurate approximation to the function's root. So here we have a graph, so you can see a little bit better what's going on. We have the red line being our function, the black line being our derivative, this black dot being our initial guess along the x-axis, another iteration being this black dot, and they slowly just move towards this red dot, which is going to be the root, what we're looking for. So let's apply the Newton Raphson method to the function negative e to the negative x minus x from the textbook. With an initial guess at 0, we find its derivative to be negative e to the negative x minus 1. The root is updated using our formula. Initially, our percent error is very high, but after a few iterations, we converge to a value close to 0.56 with minimal error. In contrast, when dealing with the function x to the 10th minus 1, the Newton Raphson method struggles. Convergence is slower, taking 40 iterations to reach an acceptable percent error. The graph illustrates that our initial guess of 40 were far from the point of the x-intercept. It goes right past our x-intercept to 50. So it takes about 42 iterations to get there. Not very efficient in this case. When forming a Python script in Google Colab for the Newton Raphson method, odds are high you'll need to import some files to aid with the mathematical portion of the code. For this example, I found the root of our first example from the book, negative e to the x minus x. For starters, I gave Newton's method a definition, allowing for the input of the function, its derivative, an initial guess, and the number of iterations we wanted to use. In this example, I defined the math e for the function as well as the derivatives of the function. Following this, I defined the equation of our root, which is equal to our initial guess minus the function over its derivative. I then printed the root and the number of iterations and plugged in my values for my Newton's method definition, the initial guess from the book, and 4 iterations, right down here. My answer was 0.56714, 4 iterations, just like the book said. However, in the next problem, it kind of amps up a little bit. Here we have a problem using a drag coefficient for a bungee jumper and free fall. We're given 7 variables: gravity, velocity, the drag coefficient. Fortunately, the book gave us the function and the function's derivative to make plugging this into Python a little bit easier. Well, maybe not that part, but not doing the derivative on our own. It did take me a bit to figure out how to manipulate this equation into Google Colab, but after some finagling, I got it. So for starters, I defined all of our variables: the gravity, our drag coefficient, the free falling in 4 seconds, the velocity at 36 meters per second, all up here. The book used an initial guess of 140 for the bungee jumper's weight, which I thought was really a good guess since the answer is 142. I tried it with 1 kilogram and 2 kilogram for guesses, and they still did converge to 140. So that didn't have as big of an impact as I thought. So right here you can see I defined the function and its derivative right here. I did use the percent error tolerance of up to 100,000th of a percent, just like the book recommended. A maximum iteration of 50. Yeah, here's our equation. Here's where I wanted this if statement here. checks to be if the found value is close to our target value based on the velocity given in the equation, essentially double checking our work. Then print the result. Here we have the same value that the book had, 142.74 roughly. In the end of the problem, I wanted to see it on a graph to look at the x-intercept of our root. Using matplotlib and numpy, I plotted the two end directions of our function lines and the prime function line along our x-axis where the mass is, and then along the y-axis, which is just a generic output for the values of the function and the derivative. So, we can see the benefits of the Newton Raphson method. It is very efficient when it converges. It usually requires fewer iterations compared to other root finding methods. It's very adaptable. The method can be adapted to find multiple roots of a function simultaneously. The applicability of the Newton's method is not just limited to any specific type of function and can be applied to a wide range of continuance and differentiable functions. And lastly, it's versatile. The Newton-Raphson method is not restricted to finding roots of equations only. It can be adapted for optimization problems and solving various types of equations. So thank you very much for watching and listening, and I hope you enjoyed.